Okay, so today we're learning about a new kind of angle that we have not talked about before, and that is an inscribed angle. An inscribed angle is an angle whose vertex is on the circle, not at the center of the circle, but on the circle, on the curved part that actually makes the circle, and its sides have to contain chords of the circle. In most cases, when we first start off, it's just going to be chords, but later on, sometimes you'll have whole lines going off the circle and stuff like that. So the intercepted arc is basically the arc that is in the interior of the angle's interior. So here, when we're talking about this angle, its intercepted arc is the part that's inside the interior of that angle. Okay? When something is intercepted, it means it's cut off, right? That's literally what it means to intercept something. So, frequently we think of it probably in terms of football. There was an interception. The defender cut off the ball from where it was intended to go. Here, this angle cuts off this arc. Sometimes they'll say that arc KD subtends angle KHD. It's the same thing as saying it's the intercepted arc. It's kind of an older usage, but you still see it sometimes from time to time. Now, unlike the central angle, the measure of an inscribed angle is half the measure of its arc. The central angle is equal to the measure of its arc, but the inscribed angle is only half. I'm going to real quickly, don't worry about writing this down at all, but let me show you an illustration of why that has to be true. So if I start with the circle, and to make it the easiest possible, I'm going to draw in a diameter. And I'm going to draw in this central angle right here. And then I'm going to have an inscribed angle like this. Okay? I can choose any angle I want for this angle. Let's say that I think it is 72 degrees. What do we know about the measure of the central angle? It's got to be 72, right? These two angles are a linear pair, so this angle has to be 108. Right? What kind of a triangle is this big obtuse triangle over here besides being big and obtuse? It's isosceles. So how can we find the measures of these two angles then if we know the vertex angle is 108? And then 180 minus 108 is 72. Split in half is 36. This inscribed angle is half the measure of its arc. It always works out that way. Now, proving it when you don't have a diameter is ugly. I picked the easy one to prove it to you by. Okay? The way I think about it is this, and I don't know if this will help you or not, but it helps me. The inscribed angle is twice as far away from the arc as the central angle is. Therefore, it's half as big. If it was 4 times further away, it'd be 1/4 as big, but it's twice as far away. That's not completely and totally mathematically accurate. I'm like, well, how do you measure how far the vertex is from the angle? Where on the angle are you measuring? And it's not quite true, but that's the way I think about it. It's further away, so the further away it is, the smaller the angle is. If I wanted to put a segment or an angle way the heck out here, like this one. Oh yeah, I can't do that, but I can. There are days when I hate this program. Do you see how this angle is even smaller than that one? The further away I get, the smaller that angle has to get in order to intercept the same arc. Okay, we'll deal with ones like this another time, but not today. So let's do some examples. Let's find the measure of arc ADE and the measure of angle DAE. Well, I'm going to do those in the opposite order. DAE is just an inscribed angle, right? Its vertex is on the circle and its sides are both chords. So the measure of that will be half the measure of its arc. So the measure of angle DAE is just going to be half of 78, which is 39 degrees. Now, here we're doing this in the opposite direction. The measure of angle ABE is going to be half of its arc, which is from A around to D around to DE. So arc ADE. The angle's 125. So what do we have to do to find the measure of the arc? I'm sorry? Yeah, we just double. So 250 is the measure of arc ADE. The angle is half the arc, so the arc is twice the angle. For this next example, they don't give you any direct measurements. However, angle D is an inscribed angle that intercepts arc EF. Angle G is an inscribed angle that also intercepts arc EF. So they have to be congruent to each other. They both intercept the same arc in that circle. So this is just 2x plus 3 is equal to 7x minus 25. So we get 28 is equal to 5x. So x is 5.6. So then the measure of angle EDF is 2 times 5.6 plus 3. See, that's 11.2 plus 3 is 14.2.
5.6 just x? That's not the angle. Oh wait, I'm sorry, no.
Okay. Any questions about that? All right, let's go on to the back. Yeah. So this is actually a corollary to the previous theorem. It says that an inscribed angle is subtended by a semicircle if and only if the angle is a right angle. So here in this circle, KAR is a semicircle, right? So what's its measure? So what's the measure of this angle? 90. That's going to come up sometimes where you have a diameter drawn in and you're like, oh, well, that means that I know that that angle is 90 immediately. Okay, which is helpful sometimes because we know lots of tricks and things we can do with right triangles. All right. And then one last theorem, and this is also a corollary. It says that if a quadrilateral is inscribed in a circle, that means that all the vertices of the quadrilateral lie on the circle, then its opposite angles are supplementary. And you're like, what the heck? That's not immediately obvious. Let me show you why it's true. Let's talk about angle J and angle M, right? Angle J is going to be half of this great big arc from A to M to E, right? You don't need to write this down. So the measure of angle J is going to be half of the measure of arc AME. On the other side, let's change colors. Angle M is going to be half, the measure of angle M is going to be half of, follow the arc out, it goes from A to J to E. So then the measure of angle J plus the measure of angle M is going to be half the measure of AME plus half the measure of AJE. Well, what do these two arcs add up to? 360. So if we take half of each one of them and add them together, we're going to get 180. That's why these two angles are always going to be supplementary. It's always the opposite angles that are supplementary to one another when you have a quadrilateral inscribed in a circle. So here's an example problem. Find the angle measures of TLMD. So notice they don't tell you anything about angle M. We're still going to be able to find its measure. So I'm going to start with two angles that are opposite one another in the quadrilateral. So angle D and angle L. So 3B plus 25 plus 6B plus 20 has got to be equal to 180. Combining the like terms, that's 9B plus 45 is 180. So 9B is 135. Turns out that B is 15. So the measure of angle D will be 3 times 15 plus 25. So it's 45 plus 25 is 70. The measure of angle L will be 6 times 15 plus 20. 6 times 15 is 90 plus 20 is 110. Notice these do actually come out to be supplementary, right? That's a way to kind of check it. The measure of angle T is going to be 10 times 15 minus 69. Let's see, that's 150 minus 69 is 81 degrees. So then the measure of angle M will be 180 minus 81 will be 99 degrees. Okay, any questions about that? Okay, tomorrow what we'll probably do is do the quiz first because the homework has nothing to do with it. I will probably cut you off. I'm not letting people take 47 minutes for a quiz. at some point. So, don't plan on taking forever on it. And then we'll go over the homework, and then you won't have any assignment over the weekend.